Hello everyone, I am Gengliang, software engineer at Databricks. I am also contributor of Apache Spark. Databricks is founded by the original team who created Apache Spark. We provide a platform that accelerates innovation by unifying data science, engineering, and business. It is powered by Spark. It is available in both Azure and AWS. This talk is part 2 of the Apache data source v2 session. Wenchen has introduced the background and design details in the previous talk before the lunchtime. This talk is to show some example for how to read and write Parquet files with the v2 API. I will also introduce some internals about how data source works. In brief, data source v2 is more extensible and made possible for more optimizations. We are migrating the current built-in data source to v2. Hopefully, we can make it in Spark 3.0. Let's see how Spark reads Parquet files. Here is a simple query example. Spark reads all the values of the column Thumbstack, which happened in San Francisco this year. To implement it, first of all, we need to understand the data so that we can read a Spark raw format. Also, we need to skip unneeded data to make the execution smarter and faster. Before we start it, let's have a quick overview. Parquet is a columnar data representation. Hierarchically, a Parquet file consists one or more row groups. A row group contains exactly one column trunk per column. The footer contains schema details and metadata about the row groups. Here is our example input data layout. The data is partitioned by the column year. In each folder, there are multiple Parquet files. Each file contains multiple row groups, and inside a row group, there are many column trunks. We can implement the logic in the main interface data source, which Wenchen already introduced. First, we find all the Parquet files, and then we read all the schema from their footers. Finally, we merge them to get a final version. In this step, we already know how to read the data in the way of single thread, so this is good. But however, reading all the data of 4 years is expensive. We noticed that the query only needs the data of this year, so that we can skip the green part, the directories of the past 3 years. Even more, as there are metadata for each row group, we can perform row group skipping. If Parquet dictionary filtering is enabled, the value set of the column city will be in the metadata. So we can skip the row groups which doesn't contain San Francisco in the column city. To implement this, we can use the mixing interface support push-down filters. For Parquet, there are 2 types of filter. One is partition filter. After we push it down, we don't need to evaluate. In our example, as we have selected the directory year equals 2018, we don't need to filter this column. Since all the target Parquet files we have selected, in this file, the column city, the value is all 2018. The other one is data filter. We can only use them to skip row groups. Not all the city column value is San Francisco in our selected row groups. So we need to evaluate again. So far we are doing well, but we can make even much better. As there are many column chunks, we don't need to read them all into Spark. All we need are two columns, timestamp and city. We need a column timestamp for the result output, of course, and we need to have the column city to evaluate filtering in Spark. To implement this, there is a missing support push-down required columns. Here we just save the required schema as a variable in the class, and we will use it later in the actual reading. So we are doing good. We already know how to read the data, but to make the execution in parallel, files should be split into partitions. So the basic idea is to treat all the files as a whole, and we split into partitions of the same size. Wenchen had introduced this flow in his session. I will give a quick overview. First of all, driver will create partitions, and for each partition, Spark will launch a read task. And Executor will do the actual data reading. Parquet file records will be converted to Spark raw format distributedly. The corresponding logic is implemented in the interface data source reader. We split files in file partitions of same size and then launch read tasks. The optimization we have mentioned before are all highlighted as green. When we make the partition, we only select the one satisfy the partition filtering. We also put out the data filter to skip row groups. And while we read row groups, we only need to read the column chunks we need. So in data source V2 API, we can implement the basic reading if we tell Spark how to determine the schema and how to plan the input partitions. To make the execution more effective, there are mix-ins we can use. For example, we can put down filters, we can put down required columns, and so on. So that's it. Let's look at how we can write Parquet files. Here is another query example. This is quite similar to the one in the previous example. We already know how to read Parquet files as Spark internal row. Now we need to figure out how they are written distributedly into file. Well, the goal is simple. We need to make parallel, and we want to make it as transactional as possible. Data source V2 API has a protocol to achieve the goal, which is quite similar to Hadoop commit protocol. And let's see how it works. Upon the write action, Spark will launch write task for each file partition. And Executor start to execute the write task. Each task writes to a different temporary path. Before the write job is committed, everything should be temporary. So reading the target path won't see any partial results. There can be multiple jobs running to write the same path. The job output file should be isolated. So we need another directory label with job ID. Task output filter should also temporary before they are committed. Files should be isolated between tasks because there can be task retry during the execution if task failed. I will explain this in the next example. When a task success, the write protocol requires the executors to commit the task. We can see that the output of the commit task are moved under the directory of job ID, and the task in progress remains temporary. And here is what happens when a task aborts. The executor will delete the path of aborted task and let the driver know the failure. Here we can see the aborted output is removed, while the committed one remains the same. After Spark is aware of the failure, Spark will relaunch the task, which will create a new temporary directory under the job ID temporary folder. After all the tasks are completed, driver will commit the job. So this is the final data layout. All the Parquet files will be moved under the result path. In brief, Spark saves output files to a temporary location. If task fails, output will be removed. If succeed, move the file to the final location. This is almost transactional. So when we are moving the data to the final location, there can be reassessed and it will get a partial result. But for HDFS, moving file is very fast, in milliseconds. So the window of failure is small. Let's see some code. Here we create a Parquet data source implementing the interface data source writer. As data is already read as Spark low, we need a mix-in support write internal low. First of all, a writer factory is created, which will be serialized and sent to executors. The factory is responsible for creating data writers. Data writers can convert the internal load into Parquet record as per the specified schema. In driver side, we need to handle job commit and job abort. Upon job commit, all committed task files are merged into the final path, as we have already explained. If task abort, we simply delete the temporary path. Here is the implementation of a Parquet writer factory. When executor receives the writer factory, a writer is created for each write task. A task contains different task ID and attempt ID, which can be used to distinguish stage output. So the task ID and attempt ID will be carried to the Parquet writer. This is the implementation of the actual Parquet writer. First of all, Spark determines the pending path, which we have shown before. Temporary path with job ID and task ID. In the method write, Spark internal load is write as Parquet record. Upon task commit, the pending task path is moved under the pending job path. Upon job abort, we can simply delete the pending path. And that's it. Thank you.
So we have a few minutes for questions. I'll just walk around with the mic. If you have questions, if you could actually queue up here, that would make it a little bit easier for me. Thank you.
Yeah. So I was curious, two things. So does this replace like Hadoop relation then? Does that no longer exist? Or is this now a different implementation of Hadoop relation?
This is like pseudo-code and explaining how the current was, how the current data source was, and how we will migrate into the
The one other thing then is so for object stores you have different like temporary is more painful. So is there any plan around better support for object stores, or are you going to leave that more up to the file systems themselves? So that you don't necessarily commit to a temporary path, and then like particularly in the job commit, having the driver try and move all the temporary files is impossible. But are you going to leave that more up? That's still up to the file system?
Can you repeat the question? Okay.
Maybe I can answer that for you. So with this V2 API, we allow the developers to implement their own commit logic. So this is just an example about how to easily implement the Parquet writer in HDFS. So for object store like S3, like other systems, the move file is very slow, and we need some other way to do it in transaction. So I think there are already some other kind of project in the ecosystem. And I think some kind of Netflix has a project to do that. Yeah. So I think we just have an API to be flexible enough to allow this to happen, but we don't do it in the open source side now.
Yeah.
Thank you, Wenchen.
Hi. So thank you for the talk. So in one slide, you mentioned when the Parquet writer writes a file and the last commit step is kind of rename and moving several files to the final directory. So there's still a short time. It still takes some time, and this makes it not fully transactional. So my question is there any way that we can achieve fully transactional? And in Databricks, in yesterday's keynote, it declared to fully support the transaction. Are you guys doing something different?
Yes, so there is a summit in last year by Liang, and he introduced how we do the DBIO, but I don't think I can explain how it works here. So it's not open source.
It's not open source, so it's only in your cloud service.
Yes, in our product.
Okay, cool. Or do you have any plan in future to put that in open source?
I need to ask Liang.
Any other questions for Gengliang? Okay.
You said that the existing logos are being migrated to V2. Does that mean V1 is going to be deprecated? Will it be around for a while?
I think Wenchen.
Actually, I already mentioned in the last session, we will not deprecate V1. We will support V1 for a long time, but just add a new interface V2 for another choice.
Yeah, V1 will still work.
All right, we have time for one last question.
Yeah, so Spark supports a lot of out-of-box data source currently. So how many of those data sources are actually to the V2 API?
So we are currently none of them are migrated, but we are like working on a file-based data source like abstraction. So which will contain all the works in this slide. So to make the migrating easier, we will create a base class for file data source. The data source V2 is like not only file data source, it contains that streaming also.
All right, let's give Gengliang and Wenchen a round of applause.